All right, continue on with chapter 15. Chapter 15, section 2. Treating smart pointers like regular references with Deref trait. Okay, cool. Implementing the Deref trait allows you to customize the behavior of the dereference operator, star, as opposed to the multiplication or glob operator. Okay. By implementing deref in such a way that a smart pointer can be treated like a regular reference, you can write code that operates on references and use that code with smart pointers too. Okay, this is just an intro to this section. But they do explicitly say that deref allows you to customize the behavior of the dereference operator. Thank you for explicitly stating that. I would have liked that earlier. You might have said it. I might have missed it. I don't know. Which is the star. And then they had to clarify that this is not multiplication or a glob operator here. It's a dereference operator. One thing that they said that was sort of interesting was that implementing deref allows you to treat things like a regular reference. But once they are treated like a regular reference, you can use those in smart pointers as well. Okay, that sounds kind of meta. It sounds a lot of meta. Let's first look at how the dereference operator works with regular references. Then we'll try to define a custom type that behaves like box and see why the dereference operator doesn't work like a reference on our newly defined type. We'll explore how implementing the deref trait makes it possible for smart pointers to work in ways similar to references. Then we'll look at Rust's deref coercion feature and how it lets us work with either references or smart pointers. Okay, I'm kind of excited. It seems as though first we're going to start off learning about how the dereference operator works, and then we're going to try to build our own box type, which we saw in the previous section. Go up, box. And then we'll take a look at how Rust does the deref coercion feature, which I believe that's done with strings, right? Because a lot of times you can use a capital S string or a lowercase s string, and it kind of does the switching for you. But yeah, more on that later. Note, there's one big difference between my box type we're about to build and the real box. Our version will not store its data on the heap. We are focusing this example on deref, so where the data is actually stored is less important than the pointer-like behavior. Okay, it's not going to be the exact replica. Box, as we know, stores data on the heap. Our example is going to store data on the stack. Meh. Following the pointer to the value with the dereference operator. A regular reference is a type of pointer, and one way to think of a pointer is as an arrow to a value stored somewhere else. In listing 15.6, we create a reference to an I32 value and then use the dereference operator to follow the reference to the data. This is our example. Sure, let's write that out. Editor, this is from the last section. No longer need you. No longer need you. And what we do need is let x equal 5. Let y equal, oh, this is all capitalized. My bad. Let x equal 5. Let y equal pointer to x. And then use the assert macros. Assert equal 5. And then assert that y equals 5. And we're using the star operator, which the star is the reference operator. They call it dereference or reference operator? Dereference operator. My apologies. Dereference operator. Why? And this should compile. Yay! It worked. The variable x holds an I32 value 5 right here. we set y equal to the reference to x right here. We can assert that x is equal to 5. However, if we want to make an assertion about the value in y, we have to use the dereference operator. So star y to follow the reference to the value it's pointing to, hence dereference. Once we dereference y, we have access to the integer value y is pointing to that we can compare with 5. And we did that here. If we try to write assert equals, if we try just to compare the 5 and the y, we will get this error. You can't compare an integer with a reference to an integer. But yeah, that makes sense. And it says the trait partial equal reference is not implemented. Huh. So there's a way of fixing that, so you can do it that way. And it looks like you have to implement the partial equal trait. Yeah. But that's not what this is about. This is about dereference operator. Comparing a number and a reference to a number isn't allowed because they're different types. We must use the dereference operator to follow the reference to the value it's pointing to. Using box T like a reference. We can write the code in listing 15-6 to use a box instead of a reference. The dereference operator will work as shown in listing 5-7. So yeah, let's see that. So instead of using the reference pointer, we use a box. And that was the only change. Verify that it still works. We're good. That makes sense. The only difference in listing 15.7 and listing 15.6 is that here we set y to an instance of a box pointing to the value in x, rather than a reference pointing to the value of x. In the last assertion, we can use the dereference operator to follow the box's pointer in the same way we did when y was a reference. Next, we'll explore what is special about box that enables us to use the dereference operator by defining our own box type. Okay? Defining our own smart pointer. Let's build a smart pointer similar to the box type provided by the standard library to experience how smart pointers behave differently from references by default. Then we'll look at how to add the ability to use the dereference operator. The box type is ultimately defined as a tuple struct with one element. So listing 15-8 defines a myBox type in the same way. We'll also define a new function to match the new function defined on box. Alright, so we're starting on implementation. Struct myBox, generic T, makes sense. Implementation, box, new, generic T, return instance of myBox, and myBox just has X in it, which is T. Cool. Let's write that out. Struct myBox, generic T, T, implementation block, pass the generic in, state who this is for, you're for myBox, T, and then down here we have, what is this called again? This is associated function, right? And then we'll define our function new x type T, and you're going to return myBox type T, generic T. And then we have myBox X. run just to see if I wrote everything correctly. Good, compiled. Here we go. We define a struct named myBox and declared a generic parameter t because we want our type to hold values of any type. The myBox type is a tuple struct with one element of type t. I guess that's this thing? Quite possibly. I don't really define tuples, but I'm guessing that's this. The myBox : new function takes one parameter of type t and returns a myBox instance that holds the value passed in. Okay, so let's try adding the main function in listing 15.7 to listing 15.8 and change it to use the myBox type we define instead of box. The code in listing 15.9 won't compile because Rust doesn't know how to dereference myBox. I see. Okay. So what they're stating is that we want to preemptively switch out this box implementation for our box, and then seemingly fix all the inconsistencies, which currently just deals with dereferencing. So change you to myBox. And I'm kind of curious to see what error they give us. myBox can't be dereferenced, which is what they have here. And there is no help. There is no help for cannot be dereferenced. Good to know. Our myBox type can't be dereferenced because we haven't implemented that ability on our type. To enable dereferencing with the star operator, we implement the dereference trait. Treating a type like a reference by implementing the dereference trait. As discussed in Chapter 10, to implement a trait, we need to provide implementation for the trait's required methods. The dereference trait provided by the standard library requires us to implement one method named deref that borrows self and returns a reference to the inner data. Listing 15-10 contains an implementation of deref to add to the definition of myBox. I see. So here, let's redo this real quick. We use the standard library ops deref. So we import the trait, and then we have to implement the trait for myBox. We have a target t, which is the inner value and the generic, and the way we get to t is function deref self pointer to t, pointer to self dot 0, which I believe is how you access the first element in a tuple. So yeah, we actually just really did just use tuples. That makes sense. So let's try this over here. Use standard library ops. I'm not sure what ops stands for. Maybe operations? I don't know. Implement deref, and then I guess we can do that right here. Implement for generic t deref for myBox. We have our type. Oh, that is lowercase. Type target, which is going to be equal to t, which is our generic. And then the function deref, which we need, which takes a pointer to self and it returns a pointer to t, which is the generic that we're using. And in this case, self.0, because it's a tuple, will return the our x, the value stored in myBox. Is there a typo in this? I don't know if there's a typo in this. Let's run it and see if it works. I'm curious. I'm pretty sure I hit enter and shift, but let me just do that again. It ran. It worked. That was all we needed. Cool. A type target equal T syntax defines an associated type for the dereference trait to use. Associated types are a slightly different way of declaring a generic parameter, but you don't need to worry about them for now. We'll cover them in more detail in chapter 19. Wow, you guys just pushed that 4 more chapters away. Okay. So just let's figure out what we know about this thing. We have type target T, and it is an associated type of which is a different way of declaring a generic parameter. And this is the generic parameter that's going to be used throughout, I assume. But it's going to be covered in more detail in chapter 19. Moving on. We fill the body of the deref method with and self.0. So deref returns the reference to the value we want to access with the start operator. The main function in listing 15-9 that calls the star or dereference operator on the myBox value now compiles, and the assertion passes, which we checked out. We ran the code and everything looked fine. Without the deref trait, the compiler can only dereference the and references. The deref method gives the compiler the ability to take a value of any type that implements deref and call the deref method to get a and reference that it knows how to dereference. Okay. So what they're stating here, very explicit, is that without the deref trait, the compiler only knows how to dereference this thing, the and sign. However, when you have the deref trait, it gives the compiler the ability to get a method that references the and, or that they know how to dereference. Continuing onward, when we enter star y in listing 15-9, behind the scenes Rust actually run. When we entered star y in listing 15-9, behind the scenes Rust actually ran this code. A pointer to the .y.dereference function call, which in our case returns and self.0. Yeah. It returns the actual reference, which is the and. That makes sense. That makes complete sense. Rust substitutes the star operator with a call to the deref method and then a plain dereference, so we won't have to think about whether or not we need to call the deref method. This Rust feature lets us write, so this is exactly what we did here, and what they were trying to describe here, but in a more wordy way. So what Rust does is it rewrites the call to y as this, which then returns a reference that can be dereferenced using the star. And that is why we have this here. This Rust feature lets us write code that functions identically whether we have a regular reference or a type that implements deref. The reason the deref method returns a reference to a value and that the plain deref outside the parentheses is star y.deref is still necessary is the ownership system. If the deref method returned the value directly instead of a reference to the value would be moved out of self. We don't want to take ownership of the inner value of myBox t. In this case, or in most cases when we're using a dereference operator. I see. So what they're explaining here is the reasoning as to why the dereference method, this thing right here, had to return a reference instead of the actual object, which would be, instead of a pointer to self, would be like self.0. And the reason for that is because of ownership. If we return just the object, then the whoever was calling or asking for this method would then take ownership of it, and then my box wouldn't own that value anymore. We don't want that. Note that the star operator replaced with a call to the deref method and then a call to the star operator just once. Each time we use a star in our code. Because the substitution of the star operator does not recurse infinitely, we end up with data of type I32, which matches the 5 in assert equals in listing 15-9. Implicit deref coerces with functions and methods. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion converts a reference to a type that implements deref into a reference to a type that deref can convert the original type into. Yeah, that makes sense. To coerce is typically to force one type to become another. So what they're saying here is that deref coercion converts a reference type to a type that implements deref into another type that deref can convert the original type into. So seemingly we're moving one type to another. Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter type in the function or method definition. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. Okay, that is really wordy, but more or less, seemingly what this is covering is the ability to, when using deref, because we have deref here, it will be able to coerce the inner type to something that is needed, or to a different type that is specified. Deref coercion was added to Rust so that programmers writing functions and method calls don't need to add as many explicit references and dereferences with and star. The deref coercion feature also lets us write more code that works for either references or smart pointers. To see deref coercion in action, let's use the myBox type we defined in listing 15-8, as well as the implementation of deref that we added in listing 15-10. Listing 15-11 shows the definition of a function that has a string slice parameter. Okay, a function that says hello. Alright? Let me finish reading so I know what I'm doing. We can call the hello function with a string slice as an argument, such as hello Rust, for example. Deref coercion makes it possible to call hello with a reference to a value of type myBox string as shown in listing 15-12. Okay, let's write this out first. So we have a function that we need to write or create, which is the hello function right here. So function hello, really standard, has a name that's going to be a pointer to a string, and we're doing a print line hello and the value, which is name. And we're just printing at the screen. It doesn't return anything. So what they're saying here is that in our main function, let's get rid of this. We can get rid of all of this actually. We can let m equal myBox new, and then we're creating a string, and this is a capital S string from Rust. I can Rust. And as you see here, this is capital S, which is different type from this. Then we're saying we can do hello, and we can pass a pointer to M. I see. This makes sense now. At least it's making sense to me. So what's happening here seemingly is this box has an inner type of string, right? So when we do a dereference to it, what we actually should get if we did a straight dereference is the capital S string. However, in the signature we have a lowercase s string, which is a different type. And because it's a different type, this is where we use the coercion, right? We're taking the capital S string and converting it to a lowercase s string for this method. That is my belief. That is what I'm sticking with. Let's see what happens. Oh, I didn't run that code. Let me take a step back. I ran it and it worked. Here we're calling the hello function with the argument reference M, which is a reference to my box string value. Because we implemented the deref trait on my box in listing 15-10, Rust can turn reference my box string into reference string by calling deref. The standard library provides an implementation of deref on string that returns a string slice, and this is the API documentation for deref. Rust calls deref again to turn the string into lowercase string, which matches the hello function definition. If Rust didn't implement deref coercion, we would have to write the code in listing 15-13, this thing down here, instead of the code in listing 15-12, the code we already wrote, to call hello, with a value of type my box string, type reference my box string. Okay, so yeah, they're just reiterating what I said. In our my box definition, we already know that our deref method just returns the inner type, which would have been a pointer to string, capital S. However, the standard library performs a deref coercion on string to convert string into a lowercase s str, which is the function definition, which is what I pointed out earlier. So hello takes in this, right? What they're stating here is that if Rust did not do it for us, this deref coercion, then we would have to write something like this each time we wanted to pass that string into hello. This is kind of ugly, so I'm kind of happy they do it for us. The *m dereferences the my box string into a string, and the pointer and square brackets ... takes a string slice of the string that is equal to the whole string to match the signature of hello. The code without deref coercion is harder to read, write, and understand with all of these symbols involved. Deref coercion allows Rust to handle these conversions for us automatically. Thank you. Thank you. I would not want to write that. Not at all. When the deref trait is defined for the types involved, Rust will analyze the types and use deref as many times as necessary to get a reference to match the parameter's type. The number of times that deref needs to be inserted is resolved at compile time, so there is no runtime penalty for taking advantage of deref coercion. Okay, so this is where it comes, this is where everything ties together. So we know that in our implementation of my box, right? Let's look at that real quick. We implement deref, and in this scenario, it is a deref to my box, which then shows it should show something like a pointer to string. But string has its own deref, and then that is called, and that's where the deref coercion is done, right? And the reason that you can do these two different derefs side by side is because Rust at compile time figures out how many times deref needs to be called, and then does it for us. Which they state right here. Rust will analyze the type used for deref as many times to get the reference to match the parameter's type. So seemingly, it did deref once, realized, hey, pointer to capital string is not what we need. So then it tried to call deref again. And then that's where it did the coercion, that's where we got the reference to lowercase str. And that's how everything worked out. I'm glad I understand that. That makes a lot more sense now. And they also note at the last sentence that there is no penalty for this, no runtime penalty, because this is all done at compile time. So what that means is that when we compile our code, the way they rewrote our code has this explicitly written out. How deref coercion interacts with mutability. Oh, similar to how you use the deref trait to override the star operator on immutable references, you can use the deref mutable trait to override the star operator on mutable references. Rust does deref coercion when it finds types and trait implementations in 3 cases. From reference to T to reference to U when T deref target U. Okay. From mutable reference to T to mutable reference to U when T deref mutable target U. And from mutable reference to T to reference to U when T deref target U. That was a mouthful. But more or less, these are the cases where deref coercion can happen. Which kind of seems like any case. I'm not sure what cases it cannot happen in. Because we have static reference, an immutable reference to immutable reference. We have a mutable reference to a mutable reference. And then we have a mutable reference to an immutable reference. And let's define the trait or the guidelines that have to be met. Okay. The first two cases are the same. The first two cases are the same except for mutability. The first case states that if you have a reference to T and T implements deref to some type U, you can get a pointer to U transparently. The second case states the same for deref coercion happened for mutable references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Oh, I see. That's the case that is missing. The case that is missing is a reference to an immutable T to a reference to a mutable U. That's the case that is missing. Makes sense. Immutable references will never coerce to mutable references because of the borrowing rules. If you have a mutable reference, that mutable reference must be the only reference to that data. Otherwise, the program won't compile. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting a immutable reference to a mutable reference would require that there is only one immutable reference to that data, and the borrowing rules don't guarantee that. Therefore, Rust can't make the assumption that converting an immutable reference to a mutable reference is possible. Yeah, I see. So, yeah, these are the 3 examples of where a deref coercion can happen, and the one that is missing, which they state here, is an immutable reference to T to a mutable reference of U, and that cannot happen because of the borrowing rules. That makes sense. So with that is the end of the video. I hope you learned something. I know I did. This now makes sense to me. Yes. If you like the video, subscribe, like, yada yada yada. Outside of that, peace.